delivered by Jochen Stiasny as a pre-recorded presentation. And the topic is sensitivity analysis of electric vehicle impact on low voltage distribution grids. And without further ado, please let's start playing the video.
1 second.
Hi, my name is Jochen, and together with my co-authors from ETH and Adaptricity, we have been performing a sensitivity analysis of electric vehicle impact on low voltage distribution grids. The guiding question for us was, how should we model EV impact on a grid? And you will find many approaches on that in literature. However, they usually come with only a limited amount of model variation. Why is that of a concern? Well, if your impact assessment highly depends on how you model something or which model you choose, you may in the end up with ill-informed decisions and wrong assessments. And to counter that, we've thought of a comprehensive sensitivity analysis to highlight which aspects of EV modeling are really the ones to pay attention to. And so we split up EV modeling into several dimensions or several aspects, and I'm going to explain how they work together and then analyze their sensitivity. Now let's start with the modeling framework. We chose a bottom-up approach where we first model single EVs. And we start with a driving pattern that says when do people leave home, when do they arrive home, and how many kilometers do they drive during that time. Then you characterize the electric vehicle by its battery capacity and its consumption per kilometer. And you have a charging or assign a charging behavior to a person or to a car. That means how often do people charge during the week. And to connect the EV to the grid, you have the charger, and that is characterized by the charging power that it can deliver. Now, we don't have a single EV, but many EVs, which is expressed in the penetration level, the number of EVs, and their placement in the grid. And together with the base load from households, for example, you end up with a total grid load. And if you know the grid model, you can then do AC power flow computation and analyze the resulting time series with respect to some metrics. For example, the peak load of the transformer is the main metric for our purpose that we will use. Now, since some of the models are not deterministic, we call this a realization of a scenario, and we perform multiple of them, such that we in the end can compute scenario statistics from all those different realizations of the same scenario. Now, the case that we looked at in particular is a Swiss distribution grid, and together with the model, we also got baseload measurements from smart meters. So there we have a reliable database. And then to model the driving patterns, we looked at the National Travel Survey from Switzerland, which is made up from combustion cars, but still for the patterns itself, it is of great value. Now, to avoid any confusion, we are looking here only at the residential area and only home charging. We also don't have or don't consider PV production separately, and all charging happens in an uncontrolled fashion. And with that, we are ready to simulate the month of January, which was the highest load by the base load, and then analyze our results. To give you an idea how all the plots that I will show afterwards come together, let's quickly walk through the creation of one. And you would start, for example, with the total EV load of a single realization. And if you add multiple realizations, you end up with a distribution of this total EV load. You can then overlay that with the base load and the transformer load. The transformer load here is simply the sum, only you need to add the losses that are created or that are occurring in the grid. And these curves will now form the basis for the first analysis of a dimension, which is the driving pattern. So let's look how different days of the week influence the results. If you contrast Mondays and Saturdays against each other, you see that over time, over the hours of the day, you have different resulting EV load, different total EV load on the y-axis. And in particular, the steep increase around 6 p.m. on Mondays really catches your eyes. Why is that? Well, if you consider the driving pattern arrival time distribution, so that means when do people arrive, typically during the day, we see a distinct peak here on Mondays, whereas on Saturdays it's a much more flat distribution. And well, that then immediately results in the sharp increase around 6 p.m. also in the total EV load on Mondays. Now, that's just a rescaling, because so far we looked at a case where there are no 11 kilowatt charges in the system. So there are two options: either you have a 3.7 kilowatt charger or an 11 kilowatt charger. Now, if we go to so that was one extreme with no 11 kilowatt charges in the system. If we go to the other extreme with only 11 kilowatt charges, we see that the driving pattern even plays a bigger role. Here you have an even larger peak and also a more distinct peak that is closer around 6 o'clock. While on Saturdays you still see an increased impact, but it is much less than on Mondays. Now, looking at the EV load alone is one thing, but if we start to add the base load and then the transformer load that we are really interested in the end, you get to another observation. That is, if you go to this slow charge or charging case with low charging powers, the driving pattern doesn't make that big of a difference. That is because the peak load in both cases occurs when the base load already dropped from its peak load again. You contrast that to the case with higher charging powers. Here the peak load of the EV and the base load coincide a lot more, and that pushes the total transformer load to much higher levels. All right, so with that I wanted to highlight how important driving pattern modeling is. You can do, if you get the arrival time distribution right, you can model it. It's not that it's impossible. You just have to be aware that it has a high impact. Okay, now let's move away a bit from this temporal way of looking at things and analyze it with respect to metrics. So we have the curves as before, and now we can look for each realization. What was the peak load? So we have the peak load of the base load in the dashed line, and then each point represents a realization of that scenario. And the box plot is just a more dense representation. Now, for the next assessment, we want to look at how much does the peak load increase from the base load to the new peak load. And well, this is in this case just a subtraction, but I plotted it down here. again, and we can compare that to the additional load, peak load, that we would get if we only looked at the EV load. And now let's bring in the number of cars that we have in our system. If we plot the penetration level, i.e. the number of cars, against this transformer load, peak load increase that we saw, and the EV load, peak load increase that we saw. And as a third dimension, you have the charger type. So how many people do have an 11 kilowatt charge? And we increase that. You see that for the transformer load, you get nearly diagonally or constantly increasing impact or additional peak load. Well, for the EV peak load, it's a bit off diagonal. To make that a bit more clear, I now normalize the y-axis with the number of cars. So now you have the additional peak load per car. And what we see now here is that for the EV loads, you see this decreasing trend in the additional peak load per car. That is because it's some form of aggregation effect, where you could say that with more larger and larger population sizes, extreme events become less likely. However, this aggregation effect does not translate into the transformer load, which is interesting. And here comes again the timing and the magnitude of the EV load into play and how that relates to the baseload peak. Because now since these two, since this changes with the penetration level, you then see only flat or a nearly constant additional peak load per car. All right, let's look at another dimension, namely the charging behavior. And with charging behavior, I mean, imagine the case that you come home with a state of charge of 70%, and you need to decide, do I charge now or don't I? And we set for each car a threshold value, and we distributed either Gaussian, which we see in other chargeable devices, or just as a reference with a flat uniform threshold. And as an extreme scenario, we say that everybody charges as soon as they come home. So as soon as they come home, they charge. And the impact we see of that is that with a Gaussian and a uniform threshold, so these two, you barely see a difference. They're just still too similar, and people still charge about 2 to 3 times a week, so that you don't actually see a large increase in transformer load. On the other hand, for the always charging, you have a lot more cars charging at the same time, and hence you see a higher impact. Now, it is a bit surprising that the 11 kilowatt, or everybody has an 11 kilowatt charger case, doesn't increase the transformer load more, and that is simply due to the fact that if you charge only your daily demand or your daily consumption, you need to charge for only half an hour, and then the overlaps between charging events reduce, which reduces the impact. And lastly, I want to look at the car type impact, meaning that you can model cars as a diverse fleet, so to speak, with large cars, small cars, medium-sized cars, or just lump them into one average car. And we don't really see a big difference here. It should not mistaken be, though, that if you increase the battery capacity of that average car or change its consumption, you still see noticeable impact. It's just more that modeling a very diverse fleet with accurate sales-based, or with a sales-based sampling, doesn't really add much to the accuracy of your model. Now that we saw all those results, what should we now look at when we model EV impact on the grid? Well, the main focus really needs to be the timing and the magnitude of the EV peak load, and it's really both of them, and how they relate to the base load. They have three main drivers for that, and for those, we believe that parameter studies are absolutely crucial to gain credibility for the assessments. Now, how can we generalize these outcomes if we don't have exactly the setup that we showed? Well, you can identify and analyze still the affected modeling dimensions if you compare what changes in your setup. So if you have PV loads, it doesn't affect the EV load directly, but more the base load, for example. And then as a small outlook, if we incorporate control strategies and look at them, we add more sensitivities and dependencies and assess, knowing in our assessment of their performance, how sensitive they are to other model choices will become very important when we judge which control strategy to use. And on that note, I'd like to close and thank you for your attention. I'm happy to take questions.
Thank you very much, Jochen, for a very crisp presentation. And now we are ready for questions. There are a couple of questions waiting for you.
Yes, I see them. Thanks. So the first question comes from Jordan. I didn't get the difference between the transformer load and the EV load. Why is the EV load smaller? So what I mean by transformer load is really the combination of the base load, so from households, and then the EV load. And since we keep the base load unaltered, I always look at the EV load separately and then add that with the additional losses to form the transformer load. And therefore the transformer load, which is just the aggregation of all loads, should also be larger. And I don't know whether I got your question then right, John. So maybe I can, maybe you can write in the chat whether that answered or not. I'll continue with the other one. That is why, or whether we look at unbalance in the low voltage grid, and we do not. So in that sense, that additional effect would come in that, so when you have different kind of charges and high EV penetration, that you would need to consider this. It was just, I think the value here would be that you could already say what models you would now need to pay attention to when you look at these unbalanced cases, such that you don't need to explore all the high dimensionality that we now did.
Thank you very much for us answering both questions very well. Thank you. I don't know if we have the opportunity to ask you, when you were designing your comprehensive framework, you select 7 dimensions, as you call them. When you were doing that design, did you look at other possible dimensions, such as weather dependency, special days, price wars, and a few other things that might come up at some point?
Yes, we were considering having other influences, though. So as you saw, we already have now 7 dimensions, and if you then for each dimension want to test models, you have to be selective in some sense to not make the scenarios really explode in number. And therefore we chose these 7 to, and I think actually with those 7 you can incorporate other models by say, what is the effect if you have charging at work, which would be, for example, that you need to charge less at home, and you could represent that by, let's say, a proxy also in these dimensions. So,
well, yes, excellent. Thank you very much, and many congratulations on your presentation.